Alright, in the previous video we were talking about the simple harmonic oscillator in which we have a mass connected to a spring and it only oscillates in the x direction. There's no external forces or energy loss mechanisms. And we arrived at the conclusion that the solution to this particular differential equation, which corresponds to the equation of motion of the system, was a simple harmonic motion. So we have the amplitude x naught corresponding to the initial displacement from the unstretched length of the spring, and some natural frequency omega naught. Now, what we're going to do in this video is we're going to analyze the energy exchange and the energy evolution over time of the system to see if it makes sense that this system is going to keep oscillating all the way throughout time. So essentially, all the way as time goes to infinity, this system will still be oscillating back and forth. There's no energy loss on the system. Let's prove that mathematically now. So the kinetic energy of the system, of any system, is just half of the mass times the velocity squared. In this case, the velocity is just going to correspond to the first derivative of this displacement function with respect to time. And it turns out that if we differentiate this over here, we get this expression in terms of a sine function. The potential energy of the system, in this case, is only dependent on the potential energy of the spring. And the energy of the spring is half of k times x squared. So if we now do the proper substitutions and we try to calculate the total energy in terms of kinetic energy plus potential energy, what we get is this. So this is what we get once we sub in that expression for the kinetic energy, so for the velocity over here. And then once we sub in the potential energy expression for the displacement here, we get this here. Now, we know that because we made this substitution when we were dealing with the differential equation, that omega naught is equal to the square root of k divided by the mass. So if we make that substitution over here, then squaring that cancels out the square root and we're left with k over m. And essentially that will cancel out the mass on this side. Now what we notice over here is that both sides of this equation have the same factor, so half of kx naught squared, half of kx naught squared. So that means we can factor that out to write the expression in this form. And from trigonometric identities, we know that sine squared of an expression plus cosine squared of the same expression is always equal to 1, which means that the total energy of the system as a function of time is always going to be half of kx naught squared. Now remember something, x naught is a constant. X naught is a constant because this is dictated by the initial displacement. Remember, we're releasing the system from rest, so we stop it at a specific extension of the spring and then release it and let it oscillate. So this is always constant, which means that the total energy of the system will remain constant throughout all of time. So there's no energy reduction, there's no energy loss, there's no energy mechanisms that are extracting anything from the system. It is always going to stay in the system. Now, how does that actually relate to this energy equivalence or energy exchange in the system? Well, if we plot the graphs for this, what we're going to see is that for the total energy, we just have a straight line over here. That makes sense because we know that the value is going to be constant as a function of time. But for the kinetic energy, we have a sine square expression. So that's going to look like this. And then the amplitude or the maximum amplitude of those oscillations are going to be dictated by this, which we know is exactly equal to this expression. So it is equivalent to this expression over here. So that's a maximum amplitude there. Now for the potential energy, we have a cosine term, which means we're going to be starting off at the maximum amplitude and then it's going to drop off and continue doing that. And the amplitude is going to be the same as it is here. Now, as you add up the two energies, you notice this one starts from 0, this one starts over here. So if you add them both, you get that value there. Now, if you go over here, for example, you notice, okay, so that's this value over here. Then I'm going to add up some value over here. So you notice that adding those two gives you the exact same constant value over here. And throughout time, it turns out that all of the kinetic energy is being converted into potential energy. And if we were to overlap these two graphs, we would see how that's indeed the case, because as the kinetic energy increases, the potential energy decreases by at the same rate. And that means that both of these are being converted back and forth at the same rate. So there's no energy lost in the system, which means that the oscillations, which we notice by plotting the graph of x as a function of time, so xt as a function of time, starting off at the initial displacement x naught it does indeed make physical sense in this case, because we assume that there was nothing external acting on the system, like air resistance or damping or friction. So it turns out that in a simple harmonic motion like this one, the system will continue to oscillate back and forth to infinity. Now, of course, we know that physically this is impossible, because even if we were to set this thing in a vacuum, there would not be anything preventing any heat from being released, because there could be friction on the wheels or on the ball bearings on the wheels. There could be friction on the surface. There could be a lot of other things acting on the system. So physically, any system that would essentially oscillate to infinity without decaying in its energy is just not physically possible. So in the next video, we're going to do is we're going to extend the analysis to a system that is more realistic and in which oscillations do indeed decay over time.